Hi there. In today's tutorial, we will learn about the risk aversion coefficient. And here's our game plan. We will first talk about what's called the absolute risk aversion, okay? And then we will move on to relative risk aversion. And at the end of the tutorial, there will be a nice exercise to test your learning, so make sure to hang around to see that. Okay, let's begin. So to understand the risk aversion coefficient, first we need to remind ourselves the typical utility function for individuals. Okay? So I plotted here two different utility functions, and there's something special about them in the sense that they are both concave. Okay, so it's maybe not so easy to notice for the blue one because it is less concave, but definitely for this orange one, you can see the concavity. So they are not linear. And this will be important because this shape actually determines the degree of risk aversion. The easiest way to think about this is that let's assume we are talking about two different people here. So let's say the first one is Adam, and let's say the next person is Sarah. Okay, so these are their utility functions. So this one, 0.2 is for Adam, and this one is for Sarah. And what this graphs really tell us that the more wealthier we are, the higher our utility. So this sort of makes sense because, as we get richer, we get, we can consume more, and that makes us happier. But that rate, right, of getting higher utility is different for Sarah and Adam. So what we would like to do is to determine their risk aversion coefficients based on these utility functions. And one final thing to note here, the type of function we have here is called a power utility function. Okay, so it has this particular general notations where we have wealth to the power of a constant, right? So, and Adam and Sarah, they have different constants. So now we can move on to absolute risk aversion, okay? So what this type of risk aversion captures is our risk aversion at a particular level of wealth, okay? And it has this particular formula where we take the first derivative of the utility function and also the second derivative, and absolute risk aversion is the second derivative divided by the first derivative with a minus sign at the start. Now, this can come across as very abstract, so let's make it more accessible. So let's remember those utility functions we had. So I think for Adam, we had wealth to the power 0.2, and for Sarah, we had wealth to the power 0.8. Okay. Now, I need to take the derivatives, right? So in general, so the derivative property we need to use is this. So this is, let's say, a typical function. If I take the first derivative, basically this power comes to the front, and then we need to subtract 1. Okay, so this is the property I need to use. So I take 0.2 as a factor to the front and subtract 1. So this becomes 0.8. So this is the first derivative, right? So this is utility prime, whereas this is utility. But I'm not done here. I need to take derivative one more time to find the second derivative. So again, I'll do the same. Put minus 0.8 to the start. So it's going to be now 0.8 times 0.2, wealth to the power minus 0.8 minus 1. Okay, so this is going to be minus 1.8. And this will be basically minus 0.16 w to the power minus 1.8. So this is the second derivative. Now I can compute the absolute risk aversion. Okay, so I begin with the minus. Okay, let's put the second derivative in the numerator, which is minus 0.16 wealth to the power minus 1.8 divided by the first derivative, which was over here, So it's 0.2 wealth to the power minus 0.8. So I can simplify this further. So this minus and minus, when you multiply them, it becomes a plus. So this disappears. If you divide 0.16 by 0.2, this is essentially 8. Okay. And now this I can move to the numerator. So it will become plus 0.8. So plus 0.8 minus 1.8 makes minus 1. Okay. So absolute risk aversion for Adam is 8 to the power, 8 divided by W for Adam, which is the W is the wealth. Okay. So intuitively, what does it tell us? It means that for Adam, his absolute risk aversion decreases as he becomes richer, right? So it means that as one person becomes wealthier, they become less risk averse. And this sort of makes sense. So for example, think about, let's say, taking on a $10,000 bet, okay? So for, let's say, a student who is about to graduate, this might be a lot of money, right? So because the student is at the start of their career, they haven't accumulated wealth and so on. So from their perspective, this is a lot of money, and they will be more risk averse about, losing this money. But then compare this with a very rich person who's, let's say, a millionaire. Now losing $10,000 is pretty much nothing to that person, right? So in that sense, this makes a lot of sense. It says that as we get wealthier, we get less risk averse. So this is absolute risk aversion. Now this is for Adam. How about for Sarah? So I'm not going to do all the steps, but I'm just going to write a final answer. So by the way, I think this has to be 0.8, right? So not 8, but 0.8. So apologies for that. Let me correct that. And for Sarah, it's going to be her absolute risk aversion is going to be 0.2. Okay. So if you compare Adam and Sarah, remember Adam had this utility W to the power 0.2 and Sarah W to the power 0.8. Basically, Adam is more risk averse because the numerator is higher compared to Sarah, right? So this is for any level of wealth, this is larger than this one. So absolute risk aversion coefficient of Adam is higher than Sarah. And to reinforce this idea even further, let's actually plot these coefficients. So let's plot the absolute risk aversion coefficient for both of these individuals. So here we have Adam, and here we have Sarah. Okay. So in both cases, as they get richer, right? So as wealth increases, they both become less risk averse, right? But Adam is always at any level of wealth, right? He is more risk averse than Sarah. So for example, when he's very poor, so his absolute risk aversion coefficient is close to 8. For Sarah, it's about 2, okay? And then, when it comes to 2, the gap closes a lot, but always Adam is a bit, for any level of wealth, he is a bit more risk averse than Sarah. Now, this captures risk aversion for a certain level of wealth. Let's now talk about relative risk aversion. So in contrast, this will capture risk aversion given a proportional change in wealth. So for example, a 5% increase in wealth. Now, in the previous case, we said that, okay, if we are poor, we'll be more risk averse about losing $10,000, right, compared to a rich person. But how about we say, as a student, let's say you face a choice where you might lose 1% of wealth. And again, a millionaire faces a choice where he or she might lose also 1% of their wealth. Now, do we expect this to be different in terms of their risk aversion? So would the student be more risk averse about losing 1% of their wealth compared to a rich person? Intuitively, no, right? So 1% is 1%. So if this guy has 1 million, essentially he is risking to lose 100,000. And if this guy has 10,000 wealth, let's say, so he's risking to lose $100. Okay, so these losses might potentially be the same, may induce the same level of risk aversion for both types of person, right? The student versus the millionaire. And with the particular functions we have chosen, the utility functions, we will see that this is indeed the case. So this time we'll talk about this relative risk aversion. And the formula will be actually very similar to the absolute risk aversion. So actually, if we look here, so this is the absolute risk aversion, including the minus sign. So all we do is that we multiply it by wealth, right? Because now we are going to look at the change in wealth. So the risk aversion given a proportional change in wealth. So that's why we insert W into the formula. So what were the absolute risk aversion coefficients? So for Adam, it was 0.8 over W, right, for Adam. And his utility function was W to the power 0.2. And for Sarah, her utility function was W to the power 0.8. And her absolute risk aversion was 0.2 divided by her wealth. Now we can write the relative risk aversion coefficients. All we need to do is to multiply by W. So this becomes 0.8 and this becomes 0.2. So as I have mentioned at the start here, so both individuals have what we call a constant relative risk aversion. So their degree of relative risk aversion is independent from the level of their wealth. So they are equally risk averse about losing 1% of their wealth, regardless of how rich or poor they are. Okay. Again, we can nicely plot this on a graph, right? So the top one is for Adam, and this one is for Sarah. Okay. So in both cases, the relative risk aversion is coefficient, but Adam, for any level of wealth, is more risk averse than Sarah. Okay. Now here is the exercise I would like you to do. So I would like you to find the absolute risk aversion coefficient and relative risk aversion coefficient for a different type of utility function, which we call a logarithmic utility function. Okay, so this is a quite popular utility function as well. So use the formulas before to find ARA and RRA. Okay. And you can find a link to the solution in the video description. So make sure to check your answers as well. Right, so that's all I wanted to cover in this tutorial. Thank you for watching. If you have enjoyed this tutorial, you'll probably enjoy the one on risk preferences as well. Again, there's a link to that in the description as well. So feel free to check that out. And I'll see you in another lesson. Bye for now.